Exercise 2. Graph the solution set of the inequality y greater than or equal to 2x plus 4. Okay, first thing we notice is that this is a linear inequality. Since we know that, then we also know the graph will be a half plane. So what we'll need is the boundary line. The boundary line equation is a y equal to 2x plus 4. Alright, in graphing this, we could size up the intercepts. If x is 0, y is 4. If y is 0, x will be negative 2. Okay, a small coordinate system will be adequate for this. Labeling axes and scaling axes. 3, negative 3, negative 3. Okay, now contrasting color for this boundary line. Again, if y is 0, x is negative 2. If x is 0, y is 4. Alright, now in sketching this boundary line, should it be a dashed or solid line? Since this equality case is part of the solution set, we have here y greater than or equal to 2x plus 4. This means we should be using a solid line. Okay, this line has the equation y equal to 2x plus 4. Now, in this case, since the inequality has the form y isolated on one side, and now we have y greater than or equal to 2x plus 4, this can be sort of read as saying we want to have the solutions be above the y equal to 2x plus 4 line with this greater than sign there. Okay, so we will shade above the line in this case. This region is the y greater than or equal to 2x plus 4. Okay, and with this solid line here, this is indicating that this line is part of the solution set here. Now, could have made a mistake. Let's get a check going here. Let's see. You know, you can do things like this as well. You could take 0, 0 and say that it's not part of the shaded region. 0, 0 is not in the shaded region, and this means, by definition, that 0, 0 is not a solution to the inequality. And the definition of not being a solution means that upon substitution into the inequality, a false statement must result. Let's see what happens. 0 for x, 0 for y. Original inequality, y, 0, greater than or equal to 2 times 0 for x plus 4. This simplifies to 0 greater or equal to 4. That is false. And that is what we wanted to see. Okay, so we actually have a check for our solution here. Alright. By the way, the reason you may choose 0, 0 to check is due to the simplicity of the arithmetic that results by letting yourself be able to have 0 for x and 0 for y. Okay. Exercise number 4. Graph the solution set of the inequality 5x minus 2y greater than 10. Okay. First thing you notice about this inequality is that it's linear. So observe the inequality to be linear. Two variables, of course. Alright, so this means that the graph will be a half plane and so what we would like is the equation of the boundary line is 5x minus 2y equal to 10. Alright, as far as graphing this goes, we could consider the intercepts. We would like to fit them on the graph, perhaps. If x is 0, y is negative 5. If y is 0, x is 2. Okay, simple coordinate system will be adequate here. Label the axes and let's scale them. 1 centimeter is 1 unit. Okay, ready for the boundary line, contrasting color, and again we had x is 0, y is negative 5, and x is 0, or rather y is 0, x is 2. Now, what do we do with this boundary line? We need to be careful when we graph a boundary line in an inequality. This inequality is strictly concerned with 5x minus y greater than 10. 5x minus 2y equal to 10, which we're graphing now, is not part of the solution set. So we must use a dashed line. This indicates this is just a reference line. These are not solutions. Okay, and this is 5x minus 2y equals 10 that we've graphed right there. Now, which side of the line do we shade? We know it's a half plane. Which side shall we shade? One way for this, in this case, is you can use a test point, and 0, 0 is very simple. Maybe we use that. So we can test 0, 0. Put it into the original inequality, see if it makes a true statement or a false statement. Okay, so we have 5 times 0 minus 2 times 0 greater than 10. That simplifies to 0 greater than 10, which would be false. Okay. Since that's false, that tells us that 0, 0 is not a solution, and that tells us that it's this side of the line that the solutions exist on. Our half plane is over here. Okay. And we label our solution set. Here we have 5x minus 2y greater than 10. Okay, now let's perform a check. Make sure we don't have any mistakes here. This is not a foolproof check, but at least it narrows down the chance of making a mistake considerably. Alright, now since we used 0, 0 already as a test point to see which side of the line to shade, let's do something else here. Let's take, it's arbitrary, but let's go let's go 4, 1, a point clearly in the shaded region. Okay, so 4, 1 is clearly in the shaded region, and this implies that 4, 1 is a solution to the inequality. Now that implies that upon substitution, a true statement must result. Let's see what happens. 4, 1, 4 for x, 1 for y. Original inequality, 5 times x, x is 4, minus 2 times y, y is 1. Is that greater than 10? Let's simplify this. This is 20 minus 2, 18, greater than 10. Oh, that's true. And that's what we wanted to see. It's a solution. Okay, so this looks good. Exercise 6. Graph the solution set of the inequality negative x over 2 minus y over 3 greater than 3. Okay. First thing I suppose we notice is that this inequality here is indeed linear. The inequality is linear. Alright, what does that mean? Well, that means we know that the graph will be a half plane. Okay, so to get our half plane going, we should consider the boundary line equation. And then when you look at this inequality, you might decide, a number of fractions and a number of negative signs. Maybe you want to algebraically manipulate things a little bit before getting started. Okay, so we want to get rid of the halves and the thirds. So we're thinking about multiplying both sides by 6, and then you also are thinking about all these negative signs. So you decide to multiply by both sides by -6. Alright, you can do that, but because it's an inequality, you got to be careful. You got to reverse this inequality sign here. So our result after multiplying both sides by -6 will be, this is now a positive and 3x. This is now a plus 2y. And now we reverse the greater than sign to make it a less than sign, and -18 appears here. Okay, so we've done that. Now this means our boundary line equation is 3x plus 2y equaling -18. Alright, in planning for this, if we were to have x be 0, y would be -9. If y is 0, x is -6. Okay, we can make a lot of room in the third quadrant and get this graph going. Okay, labeling the axes, y-axis, x on this axis, scaling the axes. 1 centimeter equals 1 unit, so 2, -3, -6, -3, -6, -9. Okay. Now, contrasting color for this boundary line. And as we had mentioned, when y is 0, x is -6. When x is 0, y is -9. Okay. Now, when we graph this boundary line, got to consider, is this are these solutions as well? The answer is no, because the original inequality is a, well, if we're looking at this version, it's a less than sign, no equals to, and the original inequality had a greater than, again, no equals. So this has to be a dashed line. Okay. You can label the equation on this dashed line. This is y equal to, I'm sorry, I meant to say this is 3x plus 2y equaling negative 18. That's what this is. Okay, now, which side of the line to shade? For that, we could test 0, 0 out and see what happens there. Test 0, 0. Let's put it into our recent inequality here and see what happens. 3 times x is 0 plus 2 times y is 0 less than negative 18. This gives us 0 less than negative 18. Well, that is false. So that tells us 0, 0 is not a solution. And since we know that this is the graph has to be a half plane, this means that it must be this side of the line where all the solutions lie. So here's where we need to do our shading. We could come in here and label, maybe we use the original inequality for our labeling here. Negative x over 2 minus y over 3 greater than 3. Okay, now, maybe there's a mistake here. It would be a little more reassuring to check things over a bit. Okay, now since we've already used 0, 0 as a test point to make a determination, I like to pick something new and unique. And perhaps we can choose, alright, let's pick something that's in our shaded region. And what I'll do is I'll think about an x-coordinate that will divide by 2 nicely, pick an even number. Okay, negative 8, and then a y that divides by 3 nicely. How about negative 8 and negative 3? It's surely in the shaded region. Negative 8, negative 3 is in the shaded region. Well, that implies that negative 8, negative 3 is a solution to the inequality. And what does that mean by definition? That means that upon substitution, into the inequality, a true statement must result. Let's see what happens. Alright, x is negative 8, y is negative 3. Again, the original inequality here for sure, because part of the check is to make sure that our algebraic rewrite didn't go astray. Okay, so here we have a negative x, negative of negative 8, that's positive 8, divided by 2. Now we have minusing a negative 3 over 3, so plus 3 over 3. How about that being greater than 3? Here's 4, here's 1. 5 greater than 3? True. And that is just what we were looking for. Okay, this looks alright. Exercise number 6. An alternative solution. Graph the solution set for negative x over 2 minus y over 3 greater than 3. Alright, it's a linear inequality. So we're expecting a half-plane graph Okay, how about that boundary line? The boundary line equation could be right here, negative x over 2 minus y over 3 equaling 3. Now, what you could do is you may notice this is awfully close to being an intercept form. Another one of the famous forms of equations, although not as famous as some of the others. Intercept form looks like x over a plus a y over b equals 1. You have to have 1 on this side. Now, this isn't in intercept form, but it's quite close. Divide both sides by 3, and it's there. We could have x over, call it negative 6, plus y over negative 9 equals 1. Now, it's in intercept form, and we can see what the intercepts would be. The x-intercept, negative 6, y-intercept at negative 9. Okay, so we're planning for quite a bit of space for the third quadrant. Label our axes. Scalar axes. 1, 2, 3, 4, 5. Negative 5. 1, 2, 3, 4. Negative 4. 5, 6, 7, 8. Negative 8. Okay. Now, to graph this in intercept form. Negative 6 as an x-intercept. Negative 9 as a y-intercept. Okay. Connect the points with a straight line. And we want to be careful because, after all, we're graphing the solutions of an inequality. It's a greater than inequality. So these boundary line solutions are not solutions to the inequality. We need to use a dashed line. Okay, this dashed line has the equation most simply, I suppose, written as a negative x over 6 minus y over 9 equaling 1. Now, what about which side to shade? Okay, for shading, we could test 0, 0. And so if we put it into the original inequality, negative 0 over 2 minus 0 over 3 greater than 3, which simplifies to 0 greater than 3, which would be false. This tells us that it's not 0, 0 side of the line where the half plane is. It's got to be the side opposite. Okay, so all of this region here becomes the solution set to negative x over 2 minus y over 3 greater than 3. Okay, let's check our work. Let's see. Alright, let's pick a point that's in the shaded region. And I'm even going to plan ahead. I'm thinking about something whose x-coordinate divides by 2 and whose y-coordinate divides by 3 evenly to make the arithmetic smooth. So maybe a negative 6 and negative 3. Negative 6, negative 3 is in the shaded region. And that implies that negative 6, negative 3 is a solution. And what's it mean to be a solution? This means upon substitution, into the inequality must yield a true statement. Okay, let's see what happens. So negative of negative 6, that'd be 6 over 2. Minusing a negative, that's plus 3 over 3. This simplifies to 3 and 1 is 4, greater than 3, true, as we wanted to see. Okay, looks pretty good. Exercise 8. Graph the solution set of the inequality y greater than or equal to 3. Okay, because this question is in an exercise set which is titled two variable linear inequalities, we know that this means we're to be graphing in the xy plane. Just in case you ever see this question out of context, you might see it written as graph in the xy plane the solution set of the inequality y greater than or equal to 3. Okay, let's continue. Well, this inequality here, it is linear. And that implies that the graph will be a half plane. Okay, the boundary line equation would be the equality case of this, y equals to 3. Alright, that's a horizontal line with a y-intercept at 0, 3. Okay, we could sketch that up easily. Label axes, x, y, scale axes. 3, I'll say 2, 4, negative 3, negative 2. Okay, now contrasting color for this boundary line. It's at y equal to 3. And let's see here, solid or dashed line. The inequality that we're graphing, the solutions of, has greater than or equal to 3, or equal to. So this boundary line is solutions as well as being a boundary line. So it'll need to be a solid line. Can label it with its equation, y equal to 3. Then the issue of shading, in this case, just by visually looking at the inequality, it wants the y to be greater than or equal to 3. Well, the y needs to be 4, 5, 6, and so on. In other words, we're going to shade above this line, this horizontal line. Okay. Label the region with its inequality here, y greater than or equal to 3. And we are pretty much set here. Let's just check things over briefly. Okay. How about 0, 0? It's not in the shaded region. 0, 0 is not in the shaded region. And that implies that 0, 0 is not a solution. And that implies that upon substitution into the inequality, a false statement must result. Okay, let's do that now. 0, 0 into that equation. 0 goes in for the y. We have 0 greater than or equal to 3. What about that? Well, that's false. As we want it to be. It's not a solution. It's supposed to do that. Okay, looks good. Exercise 10. Graph the solution set of the inequality x less than -4. Okay, because it's in the context of an exercise set whose title is two variable linear inequalities, we know we're supposed to be working in the xy plane here. But if we didn't have this exercise set, it would be unclear just what to do here, and so you might also see this question written as graph in the xy plane the solution set of the inequality x less than -4, so that you don't just come in here and decide, oh, I'll take a real number line out and put a hollow circle at x equal -4 and an arrow to the left and call that the graph, which without this statement would be normal to be expected, but we're in 2 space in this exercise set. So here we go. This inequality is linear. And this means the graph will be a half plane. We'll need the boundary line equation obtained by just taking the inequality sign and making it an equals to. Here, x equals to -4. Okay, that's a vertical line. We can sketch that. Labeling axes, x, y. Scale the axes, 3, 3, negative 3, negative 3. Okay, a contrasting color for the graph of the boundary line, x equals negative 4, a vertical line about here. Question is, solid or dashed? Well, this inequality only wants x to be less than negative 4, the equals case, not a solution, so let's make sure this is a dashed line. Okay, you can label this line with its equation, and now, by looking at this, x less than negative 4, we surely expect ourselves to be to the left of this vertical line. That's our half plane, and that's what gets the shading. Okay, this region now is x less than negative 4. And last thing we need to do is to check this over in just a moment. Okay, 0, 0. It's not in the shaded region. And that means that 0, 0 is not a solution to the inequality. And that implies that upon substitution into the original inequality, a false statement must result. See what happens. 0 for x, 0 for y. Only x is in the inequality, so 0 less than negative 4, well, that's false. Okay, and that's just what we wanted to see happen, because 0, 0 is not a solution. It should give a false statement. It does. Looks good.